So optimization and calculus of several variables. So note that last week we said for us to optimize a function, we need two conditions. So last week we said if y is a function of x, to optimize this function, the necessary condition, which is also known as a first order condition, was that for any max or mean points, dy ds should be equal to 0. So for us to maximize the function, the first order condition, the necessary condition states that we should just differentiate the function with respect to the variable and equate it to 0. So the second order condition, which is also known as sufficient condition, is the second order condition. The second order condition states that if the 2y ds squared is less than 0, then when we solve for this function, the value there, so at s is equal to a is less than 0, then a maximizes the function. However, if the 2y ds squared at s is equal to a is greater than 0, then s is equal to a minimizes the function. So it's there last week. So this is when we have just a function of a single variable. Now suppose we have z is a function of s and y. So the first order condition states that we just add one or two things, the same things, but add some things to this. So the first order condition states that so this is also necessary condition. The first order condition states that for any maximum or minimum points, and last week I said we have stationary point, we have turning points. For any maximum or minimum point, the z ds should be equal to 0, and dz dy should also be equal to 0. So if you partially differentiate this with respect to s, you equate it to 0. If you partially differentiate this with respect to y, you also equate it to 0, which is the same as this. This is just a single variable, so the dy ds should be equal to 0. Fine. But since we have two variables, we have three or more variables, you differentiate with respect to all the variables and have to equate them to 0. And that is the first order condition. The second order condition in this case is that, so this one I have to state for maximum and I have to state for minimum. So when you differentiate this with respect to s and equate it to 0, differentiate this with respect to y and equate it to 0, you have equations that you have to solve. So you solve for maybe s is equal to a value and y is equal to another value. Okay? So this sometimes ends up to become a simultaneous equation that you have to solve. So the second order condition. So for maximum for maximum, the 2z, the s square should be less than 0. So if it's just a single variable, the y squared, the s squared should be less than 0. So again, that maximizes. So for maximum point, the 2z, the s squared should be less than 0. The 2z, the y squared should also be less than 0. Then the 2z, the s squared times the 2z, the y squared minus the 2z, the s, the y, all squared should be greater than 0. For minimum point, the 2z, the s squared should be greater than 0 from here. The 2z, the y squared should also be greater than 0. And then the 2z, the s squared times the 2z, the y squared minus the 2z, the s, the y, all squared should be greater than 0. So these two conditions is the same for both maximum and minimum. What distinguishes between maximum and minimum point is that for maximum point, the second order derivatives of x with respect to x and y should be less than 0. That conforms to when you have a single variable. Then the 2z, the s squared, and the 2z, the y squared should be greater than 0 for a minimum point. That conforms with when we have a single variable. Okay? So use an example to do this. Okay. I think I'll do 2. So we have two types of optimization. We have unconstrained optimization and constrained optimization. So if we want to deal with unconstrained optimization, these are the conditions that we use. So the first, so this is unconstrained optimization. So the first order condition states that, so suppose x is a function of two variables. The first order condition states that we should just differentiate the function with respect to s and equate it to 0. We should differentiate the function with respect to y and equate that one to 0. The second order condition states that, so after doing this, you have two equations that you have to solve for s and y. So you have simultaneous equations sometimes that you have to solve for s and y. And the second order condition states that if you find the second order derivative with respect to x and you find it with respect to y and they are both less than 0, then you have what you have here is a maximum point. If you find and they are both greater than 0, then what you have here are minimum points. That is because the other conditions are the same for both, so they don't really matter. You have to check to get these conditions too. Okay. So I'll do an example. So what I'll do is I'll write the example on the board. So my boss will take the video of the example there. I'll do 2 examples from this. Then next week we'll do constrained optimization. So unconstrained optimization application. So example 1. Firm is a perfectly competitive producer that produces and sells 2 goods, G1 and G2, at 1,000 Ghana cedis and 800 Ghana cedis respectively. The total cost of producing these goods is given by TC is equal to 2 Q1 squared plus 2 Q1 Q2 plus Q2 squared, where Q1 and Q2 denotes the output of G1 and G2 respectively. Find the maximum profits and the values of Q1 and Q2 at which this is achieved. At which this is achieved. Okay, so that's the question. So, solution. So the question says, a firm is a perfect competitive producer that produces and sells 2 types of goods, that's good G1 and G2, at a price of 1,000 and 800 respectively. It means that the price for G1 is 1,000, the price for G2 is 800. So the total cost of producing these goods is given by, so for example, it can be Coca-Cola Bottling Company of Ghana. So you're producing Coca-Cola good 1, Fanta good 2. So they use the same production line and all those things. So the total cost of the firm will be the labor and the electricity and all those things they use. So that's have this function. So where K1 and Q2 are just the quantities of good 1 and good 2 produce. So you find the maximum profit and the values of K1 and Q2 at which is achieved. So the first thing we have to do is we have to find the profit function. So it's a profit function that we have to maximize in order to find the quantities that maximizes that profit. So most of the work in this question is just to find the profit function. After getting the profit function, then you apply the first and the second order conditions to find the output level that maximizes your profit. So first we'll find profit. But first we have to extract the data in the question. So in the question we are given the price of good 1. So we have P1 is equal to 1,000. We are also given the price of good 2. So P2 is equal to 800. And we are given total cost. So the total cost TC is equal to 2Q1 squared plus 2Q1 Q2 plus Q2 squared. So we know profits is equal to total revenue minus total cost. Total cost is given in the question as this. We will have to find total revenue. So we also know that total revenue is equal to price times quantity. But we have two products. So our total revenue will be total revenue from product 1 plus total revenue from product 2. So our total revenue TR will be equal to TR1 plus TR2. Then we will know that this is the definition of total revenue. Total revenue is equal to price times quantity. So when you want to find total revenue from good 1, we just have to multiply the price of good 1 by the quantity produced of good 1. Then we'll find price. The total revenue from good 2 will be price of good 2 times the quantities produced from good 2. So now TR1 is equal to P1 times Q1, which is equal to, so P1 is equal to 1,000 Q1. Then TR2 is equal to P2 times Q2, which is equal to, P2 is equal to 800 times Q2. So therefore, our total revenue, which is equal to TR1 plus TR2, is equal to 1,000 Q1 plus 800 Q2. So this is total revenue. I hope you're paying attention. Okay. So we can now find our total cost, our profit function. So you know total revenue now, and this is our cost. So just subtract total cost from total revenue, and we have our profit function. So we know profit is equal to total revenue minus total cost. So this is equal to total revenue is 1,000 Q1 plus 800 Q2. So minus, so because of the minus, you have to put the total cost function in brackets. So we have minus 2Q1 squared plus 2Q1 Q2 plus Q2 squared. So our profit is equal to 1,000 Q1 plus 800 Q2 minus, so minus affects everything, so we have minus 2 Q1 squared minus 2 Q1 Q2 and minus Q2 squared. So this is our profit function. This is our profit function. So here at this point, we cannot simplify this function. So we just leave it like this. So this is where we apply the first and the second order conditions. Okay? So finding the output level that maximizes profits. So first order conditions. So what we have to do is we have to first state the first order conditions. So the first order condition states that for any max or mean points, so here this is not z again, this is pi, then it is in terms of q1 and q2. So the pi, the q1, and note this d is not total d, this is partial derivative, should be equal to 0, and the pi, the q2 should also be equal to 0. So what you have to do is to find the pi d q1 and find the pi d q2. So we'll do that one here. So this is the function that we have to differentiate. So the pi d q1 is equal to, so we are differentiating with respect to q1. So q2 is constant. So like the 3 examples I did, if you are not getting this, go back and see how I was differentiating. So this is q1, so we are differentiating this. So just like we have y is equal to ks, dy ds is equal to the k. So that part alone. So we are differentiating this with respect to q1. So the pi the q1 will get 1,000, okay? Like this one. So we have 1,000. Then when we come here, we have 800 q2. There's no q1 here. So this will give us 0. So plus 0. In the exam, you don't have to write when you have that. Then there's q1 here. So we differentiate this. So we have minus 2. These 2 will come down to multiply this. So we have minus 4 q1. 2 minus 1 will give us to the power 1, but we don't write to the power 1. So we have minus 4 q1. Then there's q1 here. So we have minus, so since we are dealing with this q1, 2 and q2 are constant. So we have minus 2 q2. We differentiate q1 alone, we have 1, right? Then minus, there's no q1 here. So this actually gives us 0. And the law says we should equate this to 0. So this implies that 1,000 minus 4q1 minus 2q2 is equal to 0. We can send these ones to the other side, okay? So we have 1,000 is equal to, so it has positive 4q1 plus 2q2. And name this equation 1. So do the same thing for, so we've done just this part. You have this equation, so you have to differentiate the function again with respect to q2. So I'll do that one here. So we have the pi, the q2, and that is equal to, so you're different with respect to q2. So there's no q2 here. So this whole thing is 0, okay? So we have 0. Then we are different with respect to Q2. So we just get the 800 because this is just to the power 1. So we have 800. So we have plus 800. Then there's no Q2, so this is a constant. So we have minus 0, but there's no Q2 here. And when you come here, there's Q2 here. So the coefficient of Q2 is constant. So we have minus 2Q1. It's a constant. When we differentiate this, we have 1. Then 2 comes down. So we have minus 2 comes down. We have Q2. 2 minus 1 is 1, so we don't write that. The law says this should be equal to 0. So this implies that 800 minus 2Q1 minus 2Q2 should be equal to 0. So we can send this one there again. So this implies that 800 is equal to 2Q1 plus 2Q2. So this is equation 2. So what you have to do is you have to find Q1 and Q2. This Q1 and Q2 that we'll find, we wouldn't know whether they are maximum points or minimum points unless we apply the second order derivative. So you have to first find Q1 and Q2 by solving equation 1 and equation 2 simultaneously. So I'll do that by substitution. So the first thing I'll do is I'll make either Q1 or Q2 the subject here and substitute it into equation 2 to get that. So from equation 1, from equation 2, we have by making Q1 the subjects, 2Q1 plus 2Q2 is equal to 800. So since I'm making Q1 the subjects, I will send this one to the other side. So I have 2Q1 is equal to 800. Then this goes there minus 2Q2. So since I'm looking for Q1, I divide him by 2 and divide him by 2. So I have Q1 is equal to, this is 800 divided by 2, I have 400 minus 2 divided by 2 is 1. I have Q2. So this will give me equation 3. So what I have to do is to substitute equation 1 into equation I substitute equation 3 into equation 2. Okay. So substitute equation 3 into equation 1. So equation 1 we have 4Q1 plus 2Q2 is equal to 1000. Okay, so it means that whenever I find Q1, I put 400 minus Q2 there. So I have 4 into brackets Q1 is 400 minus Q2, then plus 2Q2 is equal to 1000. So this has become a simple linear equation. What I have to do first is to expand. 1600 minus 4Q2 plus 2Q2 is equal to 1000. So this will be 1600 minus 2Q2 is equal to 1000. So I'm looking for Q2. I'm good like I can send this one to that side and bring this one here. Okay? So I have 1600. This is plus, you can't have minus 1000 is equal to 2Q2. So I have 600 is equal to 2Q2. I divide here by 2 and divide here by 2. Q2 is equal to 300. So I substitute Q2 is equal to 300 into equation 3 to find Q1. So substitute Q2 is equal to 300 into equation 3. So we have Q1 is equal to 400 minus Q2. Q1 is equal to 400 minus 300. And Q1 is equal to 100. So this Q1 is equal to 100 and Q2 is equal to 300 are quantities that optimizes the firm's profits. But at this point, we don't know whether they maximize the profit or they minimize the profit. If we want to find out whether they maximum or minimize the profit, we have to apply the second order conditions. So the second order condition should mean I have to find the second order derivatives for the functions. So second order conditions. So first we have the pi dq1 is equal to minus 1000 minus 4q1 minus 2q2. Then we have the pi dq